Okay, so today we're going to be talking about implicit derivatives. So implicit derivatives are when you're taking the derivative of the entire equation, but when the variables don't match. So it's when you're taking the derivative of like y with respect to x. Okay, we've technically done implicit derivatives. We just haven't called it that. So for instance, this easy derivative right here, the derivative of y equals x squared. Now, we know that the derivative of y is dy over dx, or y prime, okay? Equals, and the derivative of x squared is 2x. So that's just our basic form. We're using the power rule, and we know the derivative of y is dy over dx. That's actually a shortcut. The power rule itself is a shortcut. It is a shortcut of the chain rule. And we do it because it's not necessary to sit there and do chain rule with this every time. So let me draw in what it would look like if we had to do this chain rule. So this is technically y to the power of 1, and this is like x to the power of 2, like that. Okay? So if we were doing this chain rule, okay, when we take the derivative of y right there, we get dy over dx. That's the derivative of the inside. Then we move the 1 out front, times y, subtract the power, and we get y to the 0. But we know that y to the 0 is 1 times dy over dx. The same thing with the x squared. The derivative of x with respect to x is dx over dx times the power rule part, where you move the 2 out in front, times x to the first power, like that. That is what it would look like if we did chain rule to both sides explicitly. And again, dx over dx, this is just 1. This is just 1. So that's why we finish with dy over dx equals 2x. Okay? So implicit's really nothing more than chain rule. Okay? So again, let's look at the derivative of y squared. So using our chain rule, and I wrote it out right here for you, okay? If you have u to the n, the derivative is n times u to the n minus 1 times the derivative of u, which is whatever is on the inside. So following that, if I'm taking the derivative of y squared, I move the 2 out in front, subtract 1 from the power, times the derivative of y. The derivative of y with respect to x is dy over dx. So that is what we're talking about when we talk about implicitly. We're going to take the derivative of y squared, and we're going to get 2y, just like if we took the derivative of x squared, we get 2x. But when we go to take the derivative of the variable itself, we're going to end up with a dy over dx because the variables don't match. We're taking the derivative of y with respect to x versus taking the derivative of x with respect to x. So if the variables don't match, we will always end up with something like this when we're done with the derivative. Okay? So for instance, I'm going to show you even with x, if I take the derivative of x squared with respect to t, okay, now my variables don't match. So again, using chain rule, I'm going to get 2x to the first power times the derivative of the inside, which is dx over dt. So again, because my variables don't match, I have x with respect to t, I'm going to end up with this type of differential there. Okay? If this were just dx, taking the derivative with respect to x, we just get 2x like we did at the very beginning. Okay? And it works for, it doesn't matter what the variable is and what we're taking the derivative with respect to. For instance, here we're taking the derivative of p, again with respect to t. So when I take the derivative of p, I'm going to get the derivative of p over dt plus the derivative of 5, which is 0, because it's a constant. And capital P we usually reserve for perimeter. So this basically is saying, well, how is the perimeter changing over time? Just like this up here is the derivative of x, how x is changing over time. Now, there's also cases here where we're implicitly taking the derivative of x and y to completely different variables. So I have x and y in my expression, but I'm taking the derivative with respect to t. So now I'm implicitly doing x and implicitly doing y. So when we take the derivative of x squared with respect to t, we're going to get 2x times dx over dt plus the derivative of y with respect to t is 2y dy over dt. So sometimes one of my variables don't match. Sometimes both of my variables have to be done implicitly. Okay? And then our last basic example is now I'm taking the derivative of y squared with respect to y. So I'm going to get 2y times dy over dy, which means this is just 2y. Because my variables match, this becomes 1, and I'm left with just 2y because the variables match. And this is like taking the derivative of x squared with respect to x. Now we're taking the derivative of y squared with respect to y. And we do a lot more of this in Calculus 3 when we do multivariable calculus, but you just need to make sure that implicitly just means when I'm taking the derivative of a variable and when I'm taking the derivative with respect to doesn't match. Okay? So let's apply this to something that we're going to be working on implicitly with equations. Those are all expressions, but often we take derivatives of equations. So the guidelines for implicit differentiation, basically you differentiate both sides of the equation with respect to x, or whatever variable they're giving you. Collect all terms involving your differential dy dx on the left side of the equation and move all the other terms to the right. So basically we're solving for dy over dx. We factor it out and we get dy over dx by itself. Because again, what we're trying to find at the end is the derivative. And most of the time our derivative is like y prime or dy over dx or f prime of x. So when we do it implicitly, we actually solve for that differential, that dy over dx. Okay, and I'll show you what we mean. So it says find the derivative of xy equals x squared plus 3. Okay, so first thing following our steps is we take the derivative of both sides with respect to x. So we're basically taking the derivative with respect to x here for the whole thing. So we're going to start with the left side. So I'll do the left side in red. Now I'm taking the derivative of x times y. So I have to do product rule. So the derivative of x is 1 times the second y plus x times the derivative of the second. The derivative of y is dy over dx. Okay? Now that's going to be equal, and now we do the other side. So the derivative of the other side is going to be 2x plus 0. Okay? Now, we've taken our derivative with respect to x on both sides. Now, what we're going to do is move any terms that don't have dy over dx to the right. So that means right here, I'm going to subtract y on both sides. When I do that, I get x dy over dx equals 2x minus y. And again, we're trying to isolate our dy over dx, which means we got, instead of multiplying by x, we're going to divide both sides by x. So divide this by x and divide that by x. And that will give me my derivative, dy over dx equals 2x minus y over x. And that's my derivative. Now, you could break that apart and simplify it a little more, but I'm just trying to get you to understand that when we're finding derivatives implicitly, at the end, you should get on one side dy over dx, and on the other side, everything else. Okay? Now, lastly, to kind of piggyback or to basically move us to what we're going to be doing next with it, okay, I have here the derivative with respect to t of a equals pi r squared. Now, you probably recall that's the area of a circle. Area equals pi r squared of a circle. So I'm going to take the derivative of this equation with respect to t. Now, in the last one, we did it with respect to x, but we can take it derivative with respect to whatever variable we want. So again, since my variables don't match, when I take the derivative of area with respect to t, I'm going to get dA over dt. Then when I take the derivative of the other side, pi, which is just a constant, times the derivative of r squared, which is 2r dr over dt. And when we simplify this a little bit, we get dA over dt equals 2 pi r dr over dt. So that should also look familiar to you. 2 pi r is circumference. So you're going to find as we go through some of these derivatives, especially implicitly, a lot of those equations that we learned when we were in elementary school and middle school for area, volume, surface area basically come from the calculus. Like, you'll see it more and more and more, especially volume to surface area. And we'll talk more about that when we get there. But implicitly, again, just basically means that whenever we're taking a derivative and the variables don't match, we end up with this type of differential being added to our derivative. Basically, it's the chain rule, that inside, that we take the derivative as normal, but then we have to multiply by the derivative of the inside, which gives us this differential.